So let's revisit this question of how the speed of light can seem constant in all reference frames. Supposing I'm on a train and I have a torch and a tennis ball. And the torch, when I shine out a burst of light, it seems to travel at the speed of light with respect to me. And when I throw my tennis ball, it seems to go considerably slower than that. Someone standing by the side of the tracks, however, will look through the window and they'll see the light traveling at the normal speed of light. So they won't have seen that change at all, and yet they'll see the tennis ball going much faster because it's adding the velocity of the train to the velocity of the tennis ball. So let's look at how these velocities actually add. So if I've got something moving in the frame S dash, let's see how it moves in frame S. So how are we going to do that? We're going to do that the same way we did our other calculations. We're going to look at two events. So the way of sorting yourself out in special relativity questions is look at specific events. So let's look at the frame S dash briefly. I won't worry about the Y's and Z's. I'll just have my time and my X dash. So in this frame, if I'm moving at a constant velocity, then let's say my tennis ball will start at the origin, then after a while it will follow a world line that's moving in a straight line, such that if I have a later time here, I can calculate the velocity of how it's traveled from this. So if this is the origin, then this point here is going to be at some later time, and my position is going to have moved just the velocity times that time. So that's very simple. That's just something moving uniformly in the S dash frame. Now what's that going to look like in the S frame? Well, in order to know that, I'm going to have to invert these set of transformations. This is a linear set of transformations, so it's just a matter of inverting the linear matrix. In fact, that's very simple because there's a symmetry between having the velocity being plus v or minus v. So if I look at S, if I just change v to minus v, I have that relationship exactly. So if I just pop that to be a plus and that to be a plus, then I have t's in terms of t dashes and x dashes. And again, the origin transforms to the origin, which is why I chose the origin as one of my points. And so this is going to be, and notice I'm giving the gamma an explicit v dependence now because I've got two velocities in my problem. The u, which is the speed of my tennis ball in the train, and I've got the v, which is the speed of the train itself. So the speed of the reference frame compared to the speed of the item in the reference frame. And in order to get the speed of this particle in the S frame, we simply take the difference between its position there and its earlier position. Remember, we're still at the origin. The origin maps the origin. This distance, that minus that, divided by the time, that minus that. And so there we have it. It's not just a factor of u plus v. We've also got this divisor 1 plus uv on c squared. Now, does it have the right units? Yes, that's velocity. This is dimensionless, so the bottom is dimensionless. So it's got the right units. It's got the right Galilean limit. So as u and v are much smaller than c, this denominator is roughly 1, and so it's just the addition of velocities. And that's exactly what we'd expect. We'd expect that if you throw a tennis ball in a train, and someone's looking at it from the side of the road, then they'll see the velocity of the ball as being the addition of the velocity of the train plus the velocity that you threw it inside the train. And so that's exactly how we expect things to work in Galilean relativity, and indeed we get that in the limit of the speed of light going to infinity, or our velocities being small compared to the speed of light. The other thing is we wanted to recover the idea that something moving at the speed of light in this train is also going to look like it's moving at the speed of light outside the train. And we can see that in that limit, indeed the velocity just stays at the speed of light.